Singularities. So in singularities, so definition, let f of z be analytic all the points in a bounded region except at finite number of points, and these exceptional points are called singularities. I think you know that analytic means it should satisfy CR equations, Cauchy-Riemann equations. So except some point it will be always satisfy the CR equations. The function f of z is said to have a regular point at z0 if f of z is analytic at z0. A point z0 is called z0 is called f of z is analytic at z0. A point z0 is called singular point of f of z if f of z fails to be analytic at z0. So here we see in singularity we have different types. So that is two types, isolated singularity and non-isolated singularity. So in isolated singularity means a singular point z0 is said to be isolated singular point of f if f is analytic in some neighborhood of z0. Otherwise z0 is called a non-isolated singular point of f. Suppose in singularity, isolated singularities we have different types, that is again removable singularity, pole and essential singularity. For example, f of z equal to 1 by z. F of z equal to 1 by z is not analytic at z equal to 0, but it is analytic at all other values of z. Therefore, z equal to 0 is called an isolated singular point t. So then second, suppose f of z equal to 1 by z minus 1. So 1 by z minus 1. So 1 by z minus 1 is not analytic at z is equal, because 1 by 0, z minus z equal to 1 means 1 by 0, it will be infinity, it is not defined. So it is not analytic at all other values of z. Therefore z equal to 1 is a isolated singular point. And then f of z equal to a removable singularity. An isolated singularity z0 of f is said to be removable if there exists an analytic function f from neighborhood of z0 to c. In other words, f of z can be extended at to z0 so that f is analytic on neighborhood of z0. For example, consider the function f of z equal to sin z by z. So is an isolated singular point at z equal to 0. By defining the limit z tends to 0, f of z equal to 1. It means removable singularity means the limit exists finitely. So the function sin z by z, limit z tends to 0, sin z by z, it is a standard limit, so that is f equal to 1. So it is a removable singularity. For example, second one, f of z equal to z square minus 1 by z minus 1 is an isolated at z is equal to 1. So again, this is by definition of by limits you can define. So limit z tends to f of z by factorization z square minus equal to z plus 1 into z minus 1 by z minus 1. Z minus 1 get cancelled. Again at z equal to 1, 1 plus 1 equal to 2. So it is a removable singularity. Pole. Next, second type, it is a pole. So here the limit z tends to f of z tends to a f of z equal to infinity. Means it is here also limits exist infinitely. So we can z equal to a is called a pole, or there exists a positive integer n such that limit z tends to a z minus a whole to the power of n into f of z equal to a not equal to 0. Then we can say z equal to a is a pole of order n. Suppose z n equal to 1, then we can say it is a pole of order 1 and simple pole. This is also called as simple pole. And if it is order 2, then it is called pole of order 2, pole of order 3 and so on. For example, f of z equal to 1 by z minus 2. 1 by z minus 2 has a pole of order 2, because z equal to 2, if you put in denominator 2 minus 2 0, then 1 by 0 it will be infinity. So you can call it as a pole of order at z equal to 2. Similarly, another example also you can give. So then essential singularity. Essential singularity, so that is, let z equal to a is a neither removable singularity nor a pole. For z equal to is an isolated essential singularity. For example, here this can give the example statement of Cassaroti-Weierstrass theorem. The statements when we are proving, you will come to know that. So that is called actually essential singularity. So now we come to know that isolated singularity, non-isolated singularity. In types of singularity, that is removable singularity, pole, and essential singularity. So in removable singularity, you know that limit exists and it is finite. In the pole, limit exists and infinitely and non-zero. And essential singularity, limit does not exist. So these are the difference of these singularities, types of singularities. Now using this, so here we discuss one theorem, that is Taylor's theorem. So in Taylor's theorem statement, that f of z be analytic in a region omega, a in the region omega, then f of z can be expanded in the form. So that is all, f of z equal to f of a plus z minus a f dash a double 1 factor z minus a whole square into f double dash a by 2 factor plus 1 n minus 1th term plus nth term, where fnz is analytic, fnz is equal to fna by n factorial. Further, fnz is also equal to, we can write 1 by 2 pi integral over the contour c f of z by z minus a n whole to the power into z minus z, where c is the circle within the center with center a and radius r. So such that, so that is modulus of z minus a less than or equal to r is contained in omega. So this is the statement of Taylor's theorem. So now proof. So we can prove that. So already it is in statement, it is given that f of z be an analytic function and radius r such that z minus a less than or equal to r. So in a given region omega and a in omega, there exists an analytic function. So that is f1z, first derivative in the region omega, such that they can define f and z equal to f of z minus f of a by z minus a, where z not equal to a. If z equal to a, then f1z is equal to f dash of a. f1z is equal to f dash of a. So by this theorem, we have an analytic function in the region omega such that, so f of z equal to f of a plus z minus a into f1z for all z in omega. Now f1z is analytic, and applying the above argument, we find an analytic function f2z such that f1z is equal to f1a plus z minus a into f2z. So therefore f of z equal to, substitute this f1z in f of z. So then f of a plus z minus a into f1z, f1a plus z minus a whole square into f2z. Similarly, repeating the same process n times, we get f of z equal to f of a plus z minus a f1a z minus a whole square f2a plus z minus a whole to the power of n minus 1 fn minus a plus so on z minus a whole to the power of n into fn of z. So where fn is analytic in the given region omega. So now this we have to differentiate with respect to z at z equal to a. So after differentiating, f dash z equal to f1a, f of a constant, it will be 0, f of a f1a plus z into 2 times z minus a into f2a plus 1 n minus 1 to z to the power of n minus 2 fn minus a plus n into z minus a whole to the power of n minus into snz fnz at z equal to a. So this z equal to a, all the remaining terms, second term onwards, it will be 0. Then you can say f dash of a equal to f1 of a. Similarly, f double dash of a equal to 2 times f2 of a. So on. In generally, we can write it f to the power of k a by k factorial into f k into a. Therefore, f of z equal to f of a plus z minus a into f dash a by 1 factorial plus z minus a whole square by f double dash a by 2 factorial plus so on. So on n minus 1 term and last nth term for z not equal to a. So it actually previously we written for z equal to a. Now further for z not equal to a, we can write it the f z last term f z minus a whole to the power f n z expressed in terms of f n z equal to 1 by z minus a into the remaining terms. So call this as equation 1. Since f of z is analytic in omega, by Cauchy's integral formula, fn of z equal to, this is, we can write it f1 by 2 pi into integral over c f of z dz by z minus z. Now in the integration we have to take where z equal to xi belongs to some same contour, and so xi is not equal to a. Thus fn z equal to 1 over 2 pi I fn xi dxi by xi minus z. So fn z equal to, you can write 1 by 2 pi I into integral over. So we know that z equal to a, z equal to xi you replace, so fn z equal to this. So then you can take common dxi by xi minus z, then f of xi by z minus a whole to the power of n minus f of a by xi minus a whole to the power of n, so on f dash a xi minus a whole to the power of, so on that n minus up to n minus 1 term. So that is by using equation 1. So now fn z equal to 1 by 2 pi I. So integral over the curve c f of xi dxi by xi minus a whole to the power of n into dz. Each term, this is common term, we multiplied here and separately we write it, that is minus, here f of a is common, integral over c, this we multiply dxi by xi minus a whole to the power of n into xi minus z plus so on up to, that is n minus 1 term. For fixed z such that z minus a less than or, we define a new function, that is g of w equal to integral over c dxi by xi minus z into w into xi minus z for w minus a less than r. So for w equal to z, g of w equal to g of z integral over c dxi by xi minus z into d minus z, because w equal to z, so it will be 0. Why it is this is by Cauchy's integral formula. Xi minus z lies outside the circle, so z minus z minus a equal to r, therefore so it will be 0. So let w not equal to z, so previously you can say w equal to z, here w not equal to z, then g of the w equal to integral over c dxi by xi minus w into d minus z. So this you have to simplify by using partial fraction. G of w equal to 1 by z minus w into, that is 1 by z minus w minus 1 by z minus z into dz. Now that is equal to, you can write it 1 by z minus w into, by using residues 2 pi into nc omega minus ncw minus nczz. So number of residuals, so that is equal to 0. So now this again we define, let phi of xi equal to 1 by xi minus z, then phi of xi is continuous on c, g of w is equal to integral over c. So then g of w, you know that 1 by, that is 1 by xi z dz equated phi of xi into dz by xi minus z, w equal to 0. Then in general you can write it gk of w, kth derivative, that is gk of w equal to for k is greater than 0. So then gk of w is equal to k factorial integral over c phi xi into dxi by xi minus w into k power of k plus 1. Hence this integral over c dxi by xi minus z into xi minus w to the power of k plus 1 is equal to 0 for all w with w minus a less than r and k is greater than 0. So therefore fn z, so we can write it 1 over 2 pi into f of xi dxi by xi minus a whole to the power of n into xi minus z. So this is the proof. So hence the theorem. So I think I am fastly explained. If any doubts is there, you can contact me, and I send to this notes also. So you refer the notes and see this explanation. So if any doubts is there, you can ask me. Thank you one and all.